All right, guys, in this video, I'm just going to go over these practice problems that I shared with you. Um, so we're wrapping up our objectives 3.1 and 3.2, which is kinetic molecular theory and gas laws. And what I wanted to do was I went through the past three AP exams, the free response AP exams. So from 2025, from 2024, and from 2023. And just on the free response section, I wanted to post the questions that would have to do with strictly 3.1 and 3.2. So kinetic molecular theory and gas laws. Now, what you'll notice is on here, like the ones that I've starred are specifically 3.1 and or 3.2, so KMT and gas laws. But some other questions on here are questions that we should already know how to answer from units 1 and 2. And there is a question if we scroll down through the document, like here, notice here I told you don't worry about this thing called KP. And really for this question, all I want you to be able to do is, given this diagram and the total pressure, be able to figure out the partial pressure of each gas. But in the video, I will briefly explain what KP is and how you would calculate it for this section. But we'll learn all about that in Unit 4 when we get to equilibrium. But right now, if you were given this information, given the particle diagram here, and given the total pressure, being able to figure out the partial pressure of each gas in that mixture, that's something we should be able to do from 3.1 and 3.2. But I am also going to answer the other questions that are on here. But your main focus, if you're trying to just focus on kinetic molecular theory and gas laws, would be just to focus on the starred questions. But again, this one, the way it's worded here, what you really had to figure out was KP. Just understand, in order to figure out the value of KP, the first thing you would do is figure out what the partial pressure of each gas is here. So that's why I threw this question on here. Okay, so not too much. So these are three different tests. So again, this was really the only two questions, C and D, from question 5 in 2025 that was strictly kinetic molecular theory and gas laws. In 2024, it was question 2A, part 2. That was really just gas laws, KMT. And then in 2023, there were two places where KMT showed up, or gas laws. And it was, this might have been question 2 or 3 on the exam, but it was whatever question was, part F. And then again, in question 5, this was a gas law question as well. So these two parts from question 5 from the 2023 exam were basically from our unit 3. So I'm just going to go over the answers to all these. And again, like if we look at the 2025 exam, part A and B, that's not from our unit 3, but this is from our unit 1. So we should be able to answer those questions. So this was question 5. This was all question 5 in 2025. So at this point, you know, if we were taking the AP exam last year, we should be able to get all 4 points from question 5 because we have covered all of this material. Okay, so just kind of thing. Now, this is just the free response. Remember, you got to do your concept checks in AP Classroom to get your multiple choice practice. So all of those multiple choice practice questions you're doing for concept check 1 in unit 3 is going to be your main focus to get the multiple choice, the way to see how College Board asks KMT questions and gas law questions in the multiple choice section. Okay, so this isn't the only time they showed up on the exam that year. It's just, this is the only time it showed up on the free response on that exam that year. Okay, so again, let's just go through it. So first they give us some dot structures of 2 different compounds. Right off the bat, the only difference is you have carbon here versus silicon here. Okay, and then part A is just what's the VSEPR, according to VSEPR theory, what's the shape or the geometry? And this is the time where you could get away with shape or geometry, but in this case for silicon, the shape and the geometry are the same around the silicon atom in this compound. So easy question. You got 4 bonds. You got 0 lone pairs around the silicon, tetrahedral. All right, so let's look at the key. I'll scroll down. So again, question 5, part A here from 2025. The shape around the silicon is tetrahedral. Okay. Then we go back to the question B. Student claims that compound Y has a higher boiling point than that of compound X, and we were given the boiling point. But the reasoning is because compound Y has stronger London dispersion forces than compound X. Okay, well, if we look at their structures, they both have that Fon bond. Okay, so they would both be polar, they would both have hydrogen bonding capabilities. And since they only have that one kind of location on the molecule where you can have hydrogen bonding between molecules, their hydrogen bonding would be similar in strength. So the difference isn't going to be the fact that this one has stronger hydrogen bonds. It wouldn't. So it's really just going to come down to the London dispersion forces. So you would agree. And the reasoning is, the reason why this would have greater London dispersion is because silicon has more electrons than carbon. It's a little bit bigger than carbon. So this molecule is going to be a little bit bigger in size, have a bigger electron cloud. But the main thing is it has more electrons, so it has greater London dispersion. So the answer to part B would be agree. Both have hydrogen bonding and really the same number of sites where hydrogen bonding could be. Like if we went back to the structure, let me go back to it here. Whoops. If we go back to the structure, like let's say this molecule had an OH group here and an OH group here and an OH group here and an OH group here, but this one only had an OH group over here. That's when this one's going to have a lot more intense hydrogen bonding because there's a lot more locations for it. But, right, we only have one OH group. We only have one OH group here. So we're only going to get similar numbers of hydrogen bonds between molecules. So the real difference is going to be the London dispersion forces. And remember, save yourself some time on the AP exam. You can just say LDFs for London dispersion. Okay. Now let's get into some current stuff that we're learning. Okay. So part C says an equal molar mixture, so equal amounts of the two compounds is heated to 82 degrees Celsius. And, you know, one thing to make a note of, 82 degrees Celsius is the boiling point of this one, okay? But it would not yet have reached the boiling point for the silicon compound, okay? Which compound will have a higher vapor pressure? So this is one of those things that you have to understand about vapor pressure. When you have two liquids at the same temperature, the one with the higher vapor pressure is going to be the one with the weaker IMFs. So higher vapor pressure means weaker intermolecular forces because at that same temperature, more particles were able to vaporize. And if you have more particles above the liquid in the gaseous state, you would have a higher vapor pressure, right? So the answer would be compound X because it has weaker IMFs, right? And that's already been established in part B. And again, when you have a lower boiling point, you have weaker IMFs, and a liquid with the weakest IMFs would have the highest vapor pressure. A liquid with stronger IMFs would have a lower vapor pressure because less particles would be able to be in the vapor state and, you know, have a pressure, okay? So now, that's really all you would have to say. So that's why I kind of have a box around here. So compound X would have the higher vapor pressure, and your justification could just be because it has weaker intermolecular forces. But if you want to take a step further, if we really remember what the definition of boiling is, the boiling point is reached when vapor pressure equals the atmospheric pressure. So if you recall, we heated it up to 82 degrees Celsius, which was the boiling point of compound X. So we know that compound X's vapor pressure at 82 degrees Celsius is the atmospheric pressure. But since we haven't heated compound Y up to its boiling point yet, we know its vapor pressure is less than the atmospheric pressure. So we know that compound Y would have a lower vapor pressure and compound X would have a higher vapor pressure. Okay, so that would be maybe another way to say it. This way, it's you have to explain, this would take a little bit more time to explain. So you really want to do the time-saving answer when you're taking the AP exam. But, writing this down, the AP reader might be like, oh, this person really knows their stuff. But really, just the higher the vapor pressure, the weaker the IMFs. Okay. So if we go back to part D was they heated it up to 198 degrees Celsius, well above the boiling points of both. So all of the molecules are going to vaporize. We're in a sealed rigid container at 12.5 liters, and we're given the total pressure, and it just says calculate the number of moles of gas particles. So all we have to do, plug into the ideal gas law, solve for N. Just remember, don't use 198 for your temperature value. Make sure you add 273 to it, and use the Kelvin temperature, not the Celsius temperature. Okay. And the other thing to remember is make sure you use the correct R value. Okay. Now, maybe this year's formula sheet only has this R value for atmospheres, and you don't get the 62.36 R value for torr or millimeters of mercury. But just remember, this is the R value for when your pressure is in atmospheres, and that's what they gave us. So remember, whenever you're using the ideal gas law, the volume has to be in liters, and they already gave it to us, but the temperature has to be in Kelvin, so we have to add 273 to that 198 value they gave us, and then we got to make sure we use the right R value. So PV equals nRT, N equals PV over RT. We plug in our numbers, we solve, and we get moles of gas. Now, let's see, so it was an equal molar sample. So that means the partial pressure of each gas is just half of the total pressure. And that means that half of these moles was compound X and half of these moles was compound Y. But if we didn't have equal moles of it, then, you don't know unless you knew how much of each one you started with. You don't know how many moles of this is compound X versus compound Y. But since we started with an equal molar mixture of the two, we know half of this moles would be compound X and half of the moles here would be compound Y. Okay. All right, so on to 2024. Okay, so they give us this chemical reaction. Note that the only gas being produced is CO2 gas. So if they're asking about any kind of pressure questions or anything like that, the only thing we would have to worry about is the CO2, because everything else would be, aqueous or, dissolved in solution or liquid. All right, but the first part is they tell us how much CO2 is produced. They tell us how many moles, and the first question here is just convert moles to grams. So that's a pretty easy answer. So all we have to do here, whoops, I think I have it on the paper itself. Yeah. So we would just take our moles of CO2, multiply by the molar mass of CO2, and that would be grams. Okay. And then in the next part, they give us so they give us the temperature, they give us the pressure, and we know how many moles were produced, right? 0.0114 moles. And so this is just plugging the information in the ideal gas law, but this time we're solving for volume, all right? So PV equals nRT, so V equals nRT over P, so we're just plugging everything in. Just got to remember, we got to convert Celsius to Kelvin, and we don't want to plug in grams into the ideal gas law, we want to plug in moles into the ideal gas law, okay? For our amount of gas value, okay? So we would just plug in our mole value. The R value I would use again would be 0.08206 because my pressure was atmospheres, and 293 Kelvin over here divided by the pressure, and we get our volume 0.219 liters. Okay, it didn't tell us to, but we could then convert this to milliliters if needed, but they wanted the volume in liters. And remember, when you solve for V, in the ideal gas law, if you don't adjust the R values at all, then V is always going to be liters for the ideal gas law. Okay. So let's go to the next one. All right. So in 2003, okay, so just kind of a quick crash course in what KP is and that kind of thing. And again, we'll really get into it in Unit 4. But K, capital K, is equal to what we call the equilibrium expression of the reaction. And normally K, the values you plug in to solve for K are molarities or concentrations. But when it's KP, what we plug in are partial pressures. So if I want to solve for the KP for this reaction, I would need to know at equilibrium, what is the partial pressure of this gas? What is the partial pressure of this gas? Now, the way we write the KP expression is we say KP equals, and it always goes products over reactants, and the coefficient becomes an exponent. So let me show you what I mean. The KP expression for this reaction would be, would be the partial pressure of this gas, right? P subscript Al2Cl6 divided by the partial pressure of this gas squared. And the reason why you're going to square it is because its coefficient is 2. So it'd be Kp equals the partial pressure of this raised to the first power, because it has a 1 coefficient, divided by the partial pressure of this gas squared. Okay, and then to solve for the value of Kp, we would need to know what this partial pressure is and what this partial pressure is. We would plug them in into this expression and solve for the value of Kp. Okay, now again, I'm not asking you to be able to do that right now. That's something we're going to discuss in Unit 4. But note that in order to actually solve for the value of Kp, we would need to know what their partial pressures are. Okay, so that would be the Kp expression for this reaction. Okay, and then they tell us, they gave us a particle diagram of the equilibrium mixture. Okay, and in part F, they tell us what the total pressure is. Well, we know that the total pressure in a system is equal to the sum of the partial pressures. So we have two gases. We have the AlCl3 and we have the Al2Cl6. Okay, so if I know the partial pressure of this plus the partial pressure of that equals the total pressure. Okay, and then we know that the partial pressure of each gas when we're at the same temperature is dependent on the number of particles that we have. So if we count the particles, the overall number of particles, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 particles. But if you notice, 1, 2, 3, 4, 5, 6, 7, 7 of the 10 particles is the AlCl3, and only 3 of the 10 particles is the Al2Cl6. Okay, so that means we know that the AlCl3 has a higher partial pressure. The Al2Cl6 has a lower partial pressure. If we had equal number of particles of each one, then each partial pressure would just be this divided by 2, right? But we know that of the total pressure, most of the pressure is coming from the AlCl3, and a small amount of that pressure is coming from the Al2Cl6. Now remember, it's based on the mole fraction. But remember, you don't need to know moles, or a mole fraction is the same thing as particle fraction. So all we have to do is do a mole fraction of AlCl3 in the mixture and multiply it by the total pressure. And then we can do the mole fraction of Al2Cl6 multiplied by the total pressure, and that'll give us the partial pressure of that one. Or as soon as we find the partial pressure of one, subtract it from the total, and that would give us the partial pressure of the other one, right? So we'd have to count the number of particles, and we'd have to see that 7 out of the 10 are AlCl3s and 3 out of the 10 are Al2Cl6. So if we do 3 divided by 10 times the total pressure, that'll give us the partial pressure of the Al2Cl6. So when we do that, the partial pressure of Al2Cl6 comes out to be 6.63 atmospheres. And then if we do 7 out of 10, 70%, times 22.1, that'll give us the partial pressure of the AlCl3, the aluminum chloride. Okay. So we solve for the partial pressures, and that's really what I would want you to be able to do at this point. But remember, now that we have the partial pressures, and if we know what Kp is equal to, this expression, all we have to do is plug those in. So we would just plug that number into there, and we would plug that number into there, and don't forget to square it, and that's how we would get our Kp. So I think I have that solved for you. So if you wanted to solve for the Kp, again, the Kp expression would be the partial pressure of this divided by the partial pressure of this squared. The partial pressure of the Al2Cl6 was 6.63, and the partial pressure of the AlCl3 was 15.5 or 15.47. So we plug that in here, and then we would just do the math to get our Kp value. Okay. Now, later on, we're going to learn what does that value mean? What does that tell us about the equilibrium and stuff like that? But we'll talk about that back when we get to Unit 4. Okay. All right. So let's get to number 5, part F. Whoops, wrong thing. All right. So sorry, number 5, part A, I, and part AII. So here they're giving us, they tell us we have a sample of HCl gas. We're stored in a rigid container. Now, again, whenever you see rigid container, that means the volume is going to stay constant. That's going to be important for part 2. Okay, so the volume is going to stay constant. They give us the pressure and the temperature. And this time they give us the Kelvin temperature, and they just say calculate moles. So we're going to go to our ideal gas law again, solve for N. Okay, so we'll say PV equals nRT, but N equals PV divided by RT. So we plug in our pressure, we plug in our volume in liters, we plug in the correct R value, we plug in our Kelvin temperature, and we solve. So we get around 1.84 moles of HCl in the sample. Okay. And then if we go to part 2, they tell us we cool the temperature down to 2.7 Kelvin, and they want us to calculate the new pressure. Now, there's really 2 ways to go about this. We could, now that we know how many moles of gas are in the container, we could use the ideal gas law, and now we're solving for P, and we're plugging in the new temperature. And now that we know the number of moles from this part, we're plugging in the moles, and we're plugging in the new temperature. The volume doesn't change, so that's still going to be a 6. And then we're just solving for the new pressure, okay? But you could also use Gay-Lussac's law, P1 over T1 equals P2 over T2, right? We know that volume is staying constant. We know that moles is staying constant. We're not changing the number of particles in the container. All we're doing is changing the temperature, and we want to know how the pressure is going to change. So we could do P1 over T1 equals P2 over T2, and we're solving for P2. Either way, you're going to get the same answer, okay? Probably the quickest way would be to do P1 over T1 equals P2 over T2, but not that much quicker. You know, it's just plugging in numbers into the ideal gas law or plugging in numbers into Gay-Lussac's law, all right? So if we plug in the numbers into the ideal gas law, the thing we'd have to remember is like, oh, we know what the moles are now. So we plug that number in for N, our R value, our new temperature, our volume still 6 liters, solve for the pressure. And remember, when you're using that R value, your pressure is going to be atmospheres. Okay. Or, right, this was P1, this was T1. We're solving for P2, and we know our new, and this is our T2. So we would just do 7.45 times 271 divided by 296 to get the same pressure. So either way you do it, you're going to get 6.82 atmospheres should be our new pressure. And remember, expect the outcome, right? Pressure and temperature are directly proportional. So if you cool down the temperature, the pressure is going to decrease. Okay. All right. So moving on to, nope, that's it. Okay. So we did it all. All right. So again, so these were the KMT questions and the gas law questions from the past 3 free response portions of the AP exam. Pretty straightforward, I think. So, just kind of understand the way the free response set up, right? Part B might be something from unit 1, and then part C is something from unit 3, and then part D is something from unit 5. So, you got to be able to bounce around from topic to topic to topic, right? And quickly. All right. So, all right. Have a great day.